Alright guys, I think you saw the title. We're going to be learning about limits. Now the cool thing about limits is that it's such a foundational part of calculus, right? Like limits are evident in integrals, in derivatives, and so if we want to approach those higher level topics, then we need to understand what a limit is, how do we work with them, and what role do they play in derivatives and integrals. So if you're ready, let's get to it. Okay, so in this video what we'll cover is explaining what a limit is, how to solve for a basic limit, and what should we do if a limit does not exist. Okay, so to explain what a limit is, first of all, I want you to consider this problem. So we have this square here that has an area of 1, okay? Now what we're going to do is we're going to draw a rectangle this time that has the same length, but we shorten the height a bit. So now it has an area of 1/2. We shorten the height by exactly half, okay? Now we'll do the same thing again. This time we are going to just make another square here that again decreases the area by half, right? Making it look like this. And then we have another square here. This will be 1/8 because we're dividing it by 2 again. And then this will have 1/16. So you get the idea. We can just continue this trend on and on until we eventually, to infinity basically. That's the idea. We're just going to continue this on and on. So if I were to write this out in terms of an equation, so it basically be 1 plus 1/2 plus 1/4 plus 1/8, and so on and so forth. So then, what does this equal? Now you might be like, how can you have a finite number when you're going to infinity, right? You're just adding stuff over and over again. So then you can't really say that you'll get a finite number. But remember, the idea with limits, and this is the whole idea, you're not at a value. You're approaching a value. It's a simple terminology difference, but it makes and breaks the entire definition of a limit. You're not at a value. What are you approaching? Okay? So it doesn't matter where you are at. It matters where you're going. That's like a life code you should take to heart. But where are you going? So then, using this little representation, this geometric representation, you'll see that this square here looks an awful lot like this one over here, this bigger square. So then, using this reasoning, we can say that if this part here, oh my god, my pen went out again. One second. So using this reasoning, we can say that if this entire thing looks the same as this square here, then this must also equal 1. So then we can say 1 plus 1 equals 2. So we can say that the area of this entire square will be 2. Now, look, if you stop at some value, right, like let's say 1 over 256, it's not going to be equal to 2. It's going to be equal slightly less than 2. But if you continue on to infinity, just keep on adding more and more values, you won't ever reach 2, but you will approach 2. And so we can say that in the end, it equals 2. Because if we're just going to keep doing this on and on and on, and it changes values every time, then we might as well just say what it equals in the end. Okay, now that we've done number 1, we can go ahead and cross that out. Okay, now we're just going to focus on number 2, and we might as well just throw in number 3 with it as well, because they kind of go hand in hand. Okay, here we have a very basic limit. We are basically taking the limit of this function x squared plus 3x minus 12. So when you have this, the simplest way to solve for a limit is to just do direct substitution. So what this limit is asking is that as x approaches 2, what does the function approach? Okay, and to see what it approaches, your best bet is to just do direct substitution. So we can do direct substitution. So now we'll say the limit as x approaches 2 of 2 squared plus 3 times 2 minus 12. And we can evaluate this. This is 4 plus 6 minus 12. It's going to be negative 2. Okay, so what this means is that as x approaches 2, the function x squared plus 3x minus 12 will approach negative 2. Now what I showed you was just a very simple limit, but let's make this a tad bit more difficult now. Let's say we're asked to take the limit of this rational function. What is the limit as x approaches 2 of x squared minus 4 over x minus 2? And again, your best bet is to do direct substitution. So we can say, what is the limit? My pen, for the third time this day, just went out again. Never mind, it came back. What is the limit as x approaches 2 of 2 squared minus 4 over 2 minus 2? And this comes out to be 0 over 0. That's not an answer. That breaks the rules of math. One, because you have something called an indeterminate form, and two, because you're dividing by 0. Okay? So when we have something like this, we have to manipulate the function in some way that allows us to directly substitute it or use some other limit that we know to apply it to this limit so we can get an answer. So what I notice is that the numerator can be not differentiated. I was going to say differentiated. It can be broken up by dots, or the difference of two squares. Okay? So what we can say is the limit as x approaches 2, not minus 2, of x minus 2 over x plus 2 all over x minus 2. So when we do that, we see we can just cancel this out, x minus 2, x minus 2. So now we have the limit, and you might see why I keep writing the limit, but it's because, remember, we're taking the limit. We're not doing direct substitution. We're taking the limit, so you have to write it again and again. You can keep a mental note to not write it again if you want, but if you're showing a work, right, you're showing work for your calculations, and you got to write the limit of x plus 2. So we sub in 2, and we get this to be 4. Wow. So even though we could not do direct substitution at first, we got an answer at the end. Right at the beginning we had 0 over 0, but now we have 4. So here's a graph of the function. And what we see is that at x equals 2, we have a hole. What that means is that there is no value for x equals 2. But remember, this is the idea of a limit. We're not getting a concrete value, okay? We're not equaling something, we're approaching something. So then what this is asking over here is that what does the function, oh my god, my voice cracked. What does the function approach as x approaches 2 from the right side and the left side? So then as I get closer and closer and closer to this hole right here, or what's the fancy word for it? This removable discontinuity, that's a fancy word for it. But as we get closer and closer to it, what is the function approach? And we've solved that. We calculated it to be 4. Okay? Now technically, this point here is undefined. Okay? So if you were to just do it here, this would equal undefined. But even though it's undefined, we're still approaching a value. Now for my last example, I want to leave you with this. What is the limit as x approaches 0 of the function 1 over x? Now this is again a rational function. If we just do plain substitution, right, because that should always be your first step, to just plainly substitute it in, we get just 1 over 0, okay? And you can't do that because you're dividing by 0. You cannot divide by 0, okay? So then what else can we do to make this more manageable in solving for a limit? And I'll tell you right now, you cannot do anything. So what you see is that at x equals 0, the function 1 over x is both going up and going down. Okay, it's going both up and down, so it doesn't approach a concrete value, right? We always wanted to approach something, but in this case, it's not approaching anything. It is approaching something, but it's just two different values that are not the same, which means that there's no singular concrete value that we want this function to approach. So what do we do with this? Well, in simple terms, we say that the limit does not exist. DNE. But, I mean, like, if we just say that it does not exist, then what about all the other functions that also have certain values at which the function approaches two different things, and so it does not exist. So what we do instead is that we restrict what we want, from what side do we want our limit to approach something. Okay, so I'll give you a new one. If I say the limit as x approaches 0 from 0 plus, okay, and I'll tell you what that means, one second, over 1 over x, okay? 0 plus basically means that we're approaching the value 0 from the right side, okay, from all the values that are greater than 0. So remember, 0 is right here, right? I'll make it a bit bigger, okay? And so what we're saying is that forget about all the stuff that's on the left side, okay? Forget about all of this. Look just from the right side. What does the function approach as we approach 0 from the right? And in this case, we see that it goes up and up and up and up, and it just continues on forever to infinity, okay? So in this case, we'd say that it approaches infinity. That's a bad infinity symbol. Positive infinity, but I don't need to write the positive for that. Similarly, you could also say it does not exist because technically infinity is not a number, it's a concept, right? When we were talking about those squares, right? We're not saying that we're going to add up an infinite amount of values because you can't do that. But we're thinking like, what happens when we do go to an infinite amount of values, okay? It's a concept. So you can also say infinity, or it, again, just does not exist. And we can say the same thing from the left side, okay? Okay, so in this case, we're saying, okay, forget about everything that's on the right side now. We're just looking at the values of what happens when we approach 0 from the left side, or from the more negative side of things, where values are less than 0. And in this case, we see the graph goes down, okay, to negative infinity. Approaches negative infinity, okay? Again, you can also say it just does not exist, because like I said, whether it's positive infinity or negative infinity, they are not numbers, they are concepts. So we see now that the limit, as x approaches 0 from the right does not equal the limit as x approaches 0 from the left. And since they don't equal each other, then that means that the limit as a whole, without plus or minus, just does not exist. So that's an important thing. We can look at stuff from different angles, okay, to figure out certain values, even if the function as a whole does not have a certain limit at a specific point. That's key. Okay, so we basically 2 and 3 were just combined into 1. Well, maybe I just skipped over 2. Alright guys, that is it for today's video. So we covered what a limit is, we've covered how to solve for a limit, and we covered what to do when a limit does not exist. So if you are content with that, I'm content with that. I hope you learned something. And if that's all, then I'll see you guys in the next video. Make sure to like, share, and subscribe. Comment down any questions you might have. That's it. I'll see you next time.